Hello everyone, I'm Ashwin from Arista Networks. I'm part of Wi-Fi TMA team. I work at the intersection of product, engineering and customer deployment, focusing on how features like MLO translate into real world impact. This section is built over the field impacts. What we are going to cover today is we will talk about the fundamentals of MLO, and then we will deep dive into SSID deployment strategy. And then we will talk about a couple of interesting demos where we will highlight what really happens in sort of interference. How the MLO behaves, how Wi-Fi 7 clients behave in terms of interference, and finally we will deep dive into an MS Teams call, how the call is happening and how this can help wireless admins to make a decision real time, right? Followed by the design considerations. So to begin with, we know there are multiple strategies available with respect to the MLO modes, a single radio solution, multiple radio solutions. We have lot of station modes available. AP is basically an STR MLMR in nature because it can transmit, receive at the same time. But at the station side, we have various modes, right? Out of all these modes, the major ones are STR, MLMR, and EMLSR, right? Which has an ability to simultaneously transmit and receive at one and multiple radios, and the EMLSR is dynamically switching between bands. So in a high level, STR MLMR gives us the aggregation benefit and the EMLSR gives us the latency benefit. So what we have seen on the field is when you have a SSID, the MLO modes actually changes a lot, right? Say for example, when you have SSID on 2.4 and 5, majority of these clients does STR MLMR, which can transmit at 2.4 and receive at 5 and vice versa, right? And the behavior goes in case of 2.4 and 6 also, where it can transmit and receive, and most of the time it does STR MLMR. But the characteristics of the MLO changes when you have SSID on 5 and 6. It does not do STR MLMR, rather it does EMLSR or MLSR in particular. So as an admin, we need to know what sort of SSID strategy we need to have on the field. Based on that, you can actually deploy your SSID strategy, right? So if you see here, when you have SSIDs on all the bands, maybe 2.4, 5, and 6, it does STR MLMR preferring 6 gigahertz. If your country supports 6 gigahertz, then basically you would it would operate in 6 having 2.4. But in a real world deployment, do we really need to have 2.4? Because 2.4 are extremely crowded in most of the campus deployments, and having 2.4 with the STR MLMR, having the aggregation benefit, it is really going to help you in the field or not, is the question, right? So when we were characterizing across top clients like iPhone, Google Pixel and all, what we have understood is the client kind of advertise certain parameters, but eventually it is not to our expectations of how from a spectrum view the things would translate to, right? So if you see from an iPhone client behavior standpoint, when you have SSIDs on 2.4 and 5, the client kind of associate using STR MLMR, but the data transfer would happen only on one band. So in this case, if you have SSID on 2.4 and 6, it would associate with STR MLMR, but data transfer would happen only on one band, which is 6, right? And then if you are going to put it to 5 and 6, then from an association standpoint, it does advertise non-STR MLMR, okay, but it will transmit at only one band. I'll walk you through the packet captures and things like that to kind of give you some heads up. But in a very high level, what we are trying to say is the client advertise one thing, and but the data transfer on the things were happening on the in a different way, right? So let us deep dive into the iPhone characteristics. What we currently see is an association request packet from iPhone 16. This packet is taken at the channel 6 gigahertz channel, maybe 37, and what you see is the under the let me highlight. So What you see here is the common the multi-link control, right? In the multi-link control, the maximum number of simultaneous link is 1, which means it has 2 radios, and it is trying to highlight your per station profile 1 and 2, right? So we are going a little deep on what it is advertising from a per station profile perspective. The link ID 0 goes to 2.4 and link ID 1 goes to 5 gigahertz, right? It is on the 5, what you see is it is advertising non-STR MLMR, whereas on the 2.4 there is it is kind of a link ID 0, but there is not much of advertisement, right? Okay. I'm not sure if it is. That's okay. Yeah. Okay, that's fine. Yeah, I mean, just trying to. So, so what we were discussing on is an iPhone. When you have SSID on 5 and 6, the behavior changes a lot, right? So when you this is a association request packet which is coming from 5 and 6, advertising EML capabilities and MLD capabilities, right? And the number of simultaneous link is 1, but it kind of advertised non-STR, right? So here is a direct packet capture between iPhone 16 and Pixel 9. What we see is with respect to the iPhone 16 behavior, it advertises saying that it is a non-STR MLMR link, but it does not support EMLSR. As you see here, it supports there is no EMLSR capability field here, whereas in the case of Pixel 9, it advertises EMLSR capability. So what it means is there are some clients, which is iPhone 16, some of them are Pixel, they both advertise as non-STR MLMR, but at the end of the day, some of the clients can fall back if AP does not support non-STR MLMR to an EMLSR, but some of the other clients will fall back to MLSR, right? So these are some of the nuances that we need to be aware of as an administrator when we are deploying Wi-Fi 7, right? Here is a huge list of clients. I'm not going to go to each of these client list, but in a high level, we kind of added a chipset here, Broadcom, Qualcomm, and we also added EMLSR, STR, MLMR, and non-STR, right? In a long story short, what we are trying to say here is iPhone 16 and a Google Pixel, which we are going to talk about much in this presentation. From an STR, it kind of like, advertise it as STR MLMR, but if you are having an SSID on 5 and 6, it is going to do EMLSR for Pixel 9, but iPhone is going to do MLSR, right? So a lot of other clients, it's kind of behave in a different way. So I'm not going to deep dive into the first, some of the demos that we have planned. Is the first one is a spectrum view of iPhone 16. In the interest of time, I'm not going to deep dive into the spectrum view, but I'm more happy to share you the slides and things like that. But what we are seeing in this 16 is when you connect to an SSID, which is in 5 and 6, from a spectrum standpoint, right, you will see energy only on one radio, not on both, right? And the client basically chooses which band it wants to transmit based on the CCA threshold and things like that. So the second demo is a spectrum view of the Google Pixel 9 during interference. So as per the MLO spec, MLO achieves significantly high throughput, low latency for enhanced reliability. But how do clients behave in an extremely high dense environment, right? So to prove that point, we kind of tested it with a Google Pixel 9. So in this case, what we are going to run, so just a second, I'm kind of I wanted to play the video, but
we just have audio.
There is no. Yeah, I think it is playing.
Is it okay?
Yeah. So what we see is the right side you have the station view where this particular client is connecting in both 5 and 6. Here is a spectrum view. In the spectrum view, when we started the test, we are seeing at 2.4 there is no energy at all. On 5 and 6, absolutely no energy before we started the test. Now we are trying to run the open speed test. What you see is energy is picking up in 6 gigahertz band. And when you move to the 5 gigahertz band, there is a little bit of energy, but not much, because there are this is a TCP test. Some of the acts are going in the 5 gigahertz. That's why you are seeing some kind of an energy. Now, here is kind of an interference tool that I use in my lab to just inject interference. Once you started the interference, what you see is a narrow band kind of an interference you would just populate on the 6 gigahertz, as you rightly see in one of the channel. But the 5 gigahertz, which was silent earlier, now you would see a lot of energy there. Right. So what it clearly proves, and then you can also see that the throughput little bit degrade because it took little time to settle down, move. But the key point to note is from an application standpoint, it is not disconnected. The call, I mean the throughput test just keep on going, but it took little bit of link switch happening, but the energy is more in 5 now as against to 6. Right. So this is one of the highlights, and then we have disabled, we have turned off the interference. So after turning off the interference, what we see is energy on 5 is cleaner now as compared to previous instance, and the throughput is also a little bit high. So what it actually transforms to, it gives us, it tells us that the modern clients, which is Google Pixel or most of these clients, it is getting the MLO benefit, and it is kind of dynamically switching links. Both AP and a station kind of understand this behavior and then smoothly, dynamically move to another link in the presence of interference, right? Which is you imagine in a case of a highly loaded system, then and you kind of dynamically switch between links based on the interference. So this is what something which we thought we wanted to highlight. And then the last demo, it is going to be very interesting. We imagine that you are in a active Teams call, and suddenly someone downloads a huge file nearby you, and your voice call deteriorates, right? And what if there is kind of an intelligence on the client which kind of sense this behavior? It knows that there is an interference in one band. What if the call goes in the other band without even you realize the things are going to be, right? So that's what we wanted to showcase in this demo, where this is a high level topology we have, where we have connecting our APs into the switch, and we have two devices, which is Pixel 8. The Pixel 8 is here, which is an MLO client, and Pixel 6 is, which is a non-MLO by nature, right? These are the two clients which is participating in this call. And then let me start this. So what you see from our CVQ UI is this particular SSID is configured in 2.4 and 5, and there are two phones. First phone is Alex and another one is Bob, right? Since it is an MLO client, we kind of put them in a link view with an, this is a kind of MLD MAC address, and then you will also see a link MAC address against to each of these clients. Now what we do is we are running the test. From the test participant perspective, there are three participants here. One is Alex, another one is Bob, and another one is me, who is kind of initiated this call. Right now the call has been initiated, and you see my colleague Bhupinder, who is acting as a Bob, and he is kind of in this call, right? And then slowly I would also try to, I will also join this call when the call, right now the call is going on, the MS Teams call is going on live, and what you see is Google Pixel 9, which is down, and then a Pixel 6, which is on the top, right? That call is going on well, right? When things are all fine, everything is fine, it is all going fine. And then now at this moment, we kind of inject the interference on 6 gigahertz where the Bob is connected, and then the Alex, the phone is connected to both 5 and 6, right? When you started the interference, what you see is you would start seeing the glitch in the Bob's phone, as you see there, but at the same time the Alex, which is an MLO client, which does not suffer much, right? This indicates that the client can dynamically understand the interference and move across. And in a quick spectrum view to prove that actually the energy is going there, you see the narrow frequency interference which we are highlighting on the 6 gigahertz. The client is smart enough to detect the interference and it moved to the other band, right? So not only that, so the next interesting part of this is we wanted to bring both MLO and the Quast telemetry together to showcase like the benefit of AI ops and how it can help the admins in a real time, right? So that is what we wanted to showcase as part of the next demo. We will quickly move on to the screen. Let me fast forward this a bit. So in this screen, what we are trying to show is the call is actually going on, right? When the call is happening, and we have the ability to detect the call real time, and then we kind of like know the Teams call is going on, and we highlight here, right? The Alex, which is an MLO client, it does not suffer with interference, but the Bob is suffering. 50% of the call is bad, and we have a live feeds for the admin, right? So in a real time, admin will get a live feeds. This feed is very important from an admin standpoint, that because it not only let the live admins know that the live call is bad, but it also tells which is the application which is bad, and from a live standpoint, it is highlighting the bad call quality, how long the call is going on, and the interference between them and all, right? So that is very important, and it not only that, we kind of like also send a live feed in terms of Slack and using the webhooks and other things, right? Admin can get a live feed on their mobile and other devices that can help admins to know what has actually happened from a root cause standpoint, and which is a top area that this call is getting affected, so that he is aware that the call is going bad, and he can proactively check what actions that he needs to take, right? So the key takeaway of this the presentation is the voice call is good for MLO compared to a non-MLO client, and the MLO took the advantage of band steering and doesn't break the call connection. For the bad calls, admin may get the live feeds, and that's what we saw with respect to the Google Meets. And both MLO, AI Ops, and the Quast telemetry come together to support the day 2 operation, helping the admins not just detect issues, but also understand and act on them in real time. So this is something which is key. And finally, we have the deployment guidelines. I just bucketized into 3 different blocks. One is SSID configuration, deployment, AP deployment, and the network block. From an SSID standpoint, we know that for Wi-Fi 7, WPA3 is mandatory. And then we need to basically decide based on the MLO modes and your client densities and what kind of client ecosystem you have to decide how you wanted to create your SSID. But one of the SSID that is very safe to configure is WPA3 transition. The reason being is, if you configure WPA3 transition, the Wi-Fi 7 clients are going to connect the MLO clients are going to connect with WPA3, and non-MLO clients can still connect in your premises, right? It applicable to both enterprise as well as the personal deployment. And then the another set of SSID which is quite common is IoT based SSID. In the IoT based SSID, WPA3 is important. We're not sure how many of the IoT SSIDs really support WPA3 at this point in time. It is safe to say, or maybe turn off MLO on them and then you can basically reimagine your SSID based on the use cases and things like that, right? And second block is the AP deployment perspective. If you wanted to rip and replace Wi-Fi 6E based AP with Wi-Fi 7, you don't have to specially do any RF design or a site survey, because whatever best practice you had followed on Wi-Fi 6, it applicable to Wi-Fi 7 from a RF standpoint, right? You don't have to do anything extra there. And then lastly, from a network standpoint, we know that we are classifying these APs into high-end Wi-Fi 7 AP versus mid and entry-level access point, right? In a high-end Wi-Fi 7, it requires a BT power because the AP has to operate in a full capacity, right? Most of the high-end access points are going to have 3 access radios, which is going to operate in 2.4, 5, and 6. Along with that, you might have a lot of interfaces like BLE interface, USB, and other whatnot, right? So to power up all those interfaces and operate in full capacity, you need to have a BT power. But if you are kind of having a mid-range or an entry-level access point, then you can use a AT-based power to bring up your access point, which may not work in full capacity, but it can work in a limited capacity. So that is something that you can, based on your needs and wants, you can design your network accordingly. From the optimal throughput perspective, when you are migrating from Wi-Fi 6 to Wi-Fi 7 or any legacy protocol to Wi-Fi 7, you need to watch out for your backend switch. All right, the backend switch should have a multi-gig capability, maybe 2.45 or maybe 10 gig. You can also take the benefit of link aggregation if you have dual Ethernet in your access point, so that you can pump more traffic. Given that MLO has a lot of high rates from the wireless standpoint, so the Ethernet link should also have a better capability to send and support your backhaul. Yeah. And lastly, from the cable perspective, you should think of deploying Cat6a to check that. Yeah.
Thanks, Ashwin. We can take questions. The mic runners are here. Please raise your hand. If you have a question for Ashwin, please put up your hand. Mic there, please. I'm going to just shift this. You don't need a presentation.
Yeah, I don't need it.
Yeah,
Yes.
when it comes to that interference testing, right, with the Pixel 6 and Pixel 8, sorry, Pixel 9, does it actually change the band from one to another when we have interference? Because there is a band steering also works out, right?
Right. So the whole point of the phone having associated in EMLSR for this particular test tells that at the time of association, you are basically associated to both the links. But the client will be smart enough to understand the interference. Both client and access point are smart enough to understand the interference and dynamically switch from one band to another band without losing the application connectivity. So that is why it is very key to deploy more and more devices in Wi-Fi 7, get the benefit of this latency in case of dynamicity of moving from one band to another band without disconnecting the client. In a legacy clients, in a legacy system, what would happen when you are getting an interference? Right? When you are getting an interference, the client would basically disconnect and search for the new access point around, right? But here, with respect to Wi-Fi 7, you don't need to disconnect the client because the client is already associated in both links. That's why it kind of uses the dynamic nature.
You can keep putting up your hand so that the other mic runners can come. So if you have, we can take a couple of more questions. So put up your hand.
Hi, John here. So in the last slide, I can see that the AP was running in .380 power. So that requires a lot of power for the AP. So during these tests, were you able to observe a considerable battery drain in Pixel 9 and the iPhone 16 that you are using?
Sorry, I didn't. So you are basically saying in the 80 power, is there any difference?
No. The APs are running at a high power since it's 80. I was just concerned about the client power. So on the client side, were you able to observe a lot of power drain during these tests?
Yes. So basically, this is like a single one client, two client test we are running inside the RF chamber. So usually we kind of don't focus much on the client power behaviors because this is a very test which was conducted inside the RF chamber. But certainly when you are going to run a very high power test, it is expected to drain the battery because the transmission and reception happening at the client, it is in a very high speed that it does not make the client to go in a power save mode at all, right? So that way the battery may get drained faster. Yeah.
Yes, one more question.
Hi, so what was our sample size for this testing? Did we test with one device or we had multiple set of devices for our testing?
Yeah, so which sample size you are talking with, on the demo 3 or the demo 2?
So in general, because my question is, It seems that when we have multi-links, rather than having an aggregation, it acts like a redundancy. In case if there is interference in one band, we will switch to a different band. There is no aggregation in this case, where client will send and receive in both the bands.
Right. That is one of the key point that you brought. You asked for. See, the thing is, what is happening is when you have SSID on 2.4 and 5, right, you basically get the aggregation benefit. But from a deployment standpoint, right, you basically don't, some of the cases where in 5 and 6 you are deploying, the client does not do STR-MLMR there. It does only EMLSR, where it kind of dynamically switch between the bands. It is ideally, if you look into that table, the last client which was highlighted down, which is the Qualcomm client, which can do STR-MLMR in 5 and 6 gigahertz band also. It can concurrently transmit and receive, but not all the clients are capable of doing that. So that's why, since it's not actually required to do aggregation benefit always. You can also get the steering benefit in some of these deployments, right? In that case, also it is much better.
Thank
Okay.
you.
So thank you, Ashwin.
Yep.
So